Now in this video, we will consider functions of several variables. Okay, actually, I will generalize this a little bit. So far, we only considered functions defined on reals into reals. That was the topic of Calculus 1. Now, we will increase dimensions on both sides. Well, we already know from our elementary educations some functions of several variables. So, for example, let us consider the volume of, say, a cone, or rather a cylinder, maybe that's easier. Okay. Clearly, it is pi r square h. Well, that's volume. Now, here r and h are not dependent on each other. Okay. We can increase or decrease any of them without touching the other one. So, okay, we can regard it as a function of a pair, where this point is from the domain of V. Now, where is this domain? Of course, in R2. So we take a point from R2, a pair, and put them in the equation. Clearly, the order is important, because if you change H and R, of course, you don't get the same volume. And so, indeed, this is an element of R2. It's an ordered pair. Now, what's the domain of V in this example? Can we put any pi, any r, or h in this function? Well, we can, of course, but if h is negative, we will get a negative result, which does not make sense. So, in practice, in geometry that is, okay, we define V, okay, not from all of R2, but where R and H are not negative. That's to say, from the first quadrant. In R2 into real numbers. So if you put a pair that's R and H are non-negative in the formula, well, you get the volume of your cylinder, which is a number at the end. So this is a function from a part of a subset of R2 into R. Okay. We can generalize this, of course. So we can define functions of two variables. Okay. Let me give you some examples, rather. The question is, find the domains of the following functions. Okay. The first one will be, of course, we usually write z, but that's not necessary. Say it is defined as square root of xy. Now, this indeed is a function from R2 into R. It takes a point from R2, multiplies them, and takes the square root, which is a real number, and it gives us that real number. Well, what's the domain? First of all, the domain of f is a part of the plane. It's not in real numbers. So the domain will be here. Okay? when is this well defined? That's the question. That is, for which pairs xy can I talk about the square root of xy? We are in real numbers, so the only restriction is that if xy is negative, this is not possible. Well, x times y is negative if we are in the second or the fourth quadrants. So, the domain is then the axes included, also the first quadrant and the third quadrant. Both can be negative, this is well defined. Both can be positive, it's well defined. So this is domain F. Okay. A second, slightly different example is find the domain of the square root of x squared plus y squared minus 1 plus 3 square root of 4 minus x squared plus y squared. Okay, here we have the same restrictions. We only have square root. That's the only problem. Well, which number pairs can you put in this square root like this? Clearly, x squared plus y squared must be greater than 1 or equal to 1. And at the same time, it must be smaller than 4, because otherwise, the inside part of one of the roots will be negative. So, okay, it is defined only if x squared plus y squared is between 1 and 4. Both of them must be defined. Well, this is then, okay, the following. We have a circle of radius 1. We have a circle of radius 2. Okay, and this is the domain. Okay. As a third one, I will not solve it as an exercise. Find the domain of f of xy equal to, say, arc sine of x over y. Now, here we don't have a root type restriction of positivity and negativity, but x over y, okay, cannot be bigger than 1 or smaller than minus 1. Because arcsine is defined between minus 1 and 1. But at the same time, y cannot be 0. So, sketch it carefully. It will be part of the plane. Okay. The next question that we will discuss are graphs. Recall that if f is a function from a to b, need not be number sets, but they can be anything, then graph of f, okay, let me say graph of f, is defined to be the set of x f of x, where x is in the domain of f, and the first one is in A, the second one is in B, so the whole thing is in A cross B. Okay. This is the standard general definition of the graph of any function. Now, in our case, okay, we consider functions from reals into reals, or plane into space, or space into reals, whatever. So we only have real numbers. So consider a function from reals into reals. It can be part of the reals. That's not the question here. Okay. Then graph of f is a subset of R2. Well, we are well familiar with this fact. Any function from real into reals, like f of x is x squared, has a graph which looks like a nice curve in R2, but it's in R2. It's part of R2. Well, if f is from R squared into R, then graph of f is in, okay, R2 cross R, which is R3. It must be in space. The graph must be in space. Or, if we have a function, we will not consider these right now too much, but if we have a function from reals into R2, that means for every scalar number, you get a vector in plane. Okay? Then, the graph of f is still in R3. Okay. Now, does that mean they have the same character? No. There will be a big difference between them because of the dimensions in the domain and the range. And clearly, okay, for f defined on R2 into R3, or R2, or from R into R3, etc., such that the sum of dimensions is bigger than 3, okay, for such functions, or in general, if the dimensions add to something bigger than 3, could be 4 or more, okay, then we cannot sketch them. Simply because we can visualize, not imagine, but visualize, okay, only up to dimension 3 inclusive. Okay. So, at least location-wise, our dimensions are restricted to 3, not anymore. So we cannot sketch 4-dimensional things. Well, so we will not bother about these things because we cannot sketch them. We already considered the first case, so we have only 2 cases remaining, which we can sketch. Okay, let us consider the third one first. So let f be from R into R squared. Well, how do we make pictures of graphs? Well, clearly, we do it by, as we know from the first case, by putting the domain and the range in a perpendicular way. So, okay, here the domain is real numbers, range is real numbers. We put them in a perpendicular way. We have x's and y's. And then we find x comma y. Well, it's the same argument here, but it's a little bit tricky. We have a real line. This is domain. And on it, we put a perpendicular plane. Well, this is possible only if you put it in a perpendicular way like this. So what happens? Given a number, real number here, this function gives us a point in R2, in plane. So that's the value. Okay. Because of perpendicularity and because we show graphs, it will be on top of x. So this is f of x, but it is a vector now, because it's in plane. For a different x, the same thing happens. On the perpendicular plane, we have some point. Okay, it's on top of x, it's perpendicular, but this is now f of x1, it's a vector again. Continuing this way, okay? What is the set of all these points in space? Put these points together. Say, in a nice way. Okay, do it in a continuous manner. Say, if we increase x a little bit, we have a point somewhere. If we increase it, we have a point somewhere. Put these points together. So what we get is a curve. Okay. So the graph is a curve. In space. Okay. We will not be dealing with these right now. A little bit later, we will consider them in more detail. So let us now consider the remaining case, which we can make a picture of. So now, let f be from R2 into R. Okay. Then, now this is a case with which we are more familiar. The domain is R2. Okay. That's the domain. And we draw a perpendicular to it. Okay. That's the range, R. Now, the function says that for every point in here, on top of it, okay, on top of it, we have, say these are x's and y's. For every point here, on top of that, okay, we have a height, that is the z value. So this height is, I mean, not as a distance, it can be negative, okay, but that's the z value, is f of xy. Okay. So now imagine, of course, this z value is like this. This is f of xy. It can be negative, no problem, but this is perpendicular. So, for every point xy in the domain, we get a height, negative or positive. We reach a point. Now that point is xy, comma, z. So it's in the graph. When we do this, for every point at the bottom, okay, imagine from the ground, you take a point, on top of it you have something all the time. Connect them together, you get a surface. So, putting xy's and f of xy's together, it is in R3 of course, okay, we get, putting these together, we get a surface. Okay, so the graph of such a function is a surface. Well, we already considered, when we considered quadrics, such examples, but I will just go on with two more. Okay, sketch the graph of f of xy equal to 1 minus x minus 1. Now, this is a degree 1 polynomial, okay? We want to sketch its graph. Well, the graph is, of course, the following. Now, we recognize this equation. Okay, and we get, of course, a plane. Now, sketching a plane may be problematic But in some cases, especially if you can show it on top of one of the quadrants, okay, by imagination, we can extend it in all directions. So here, okay, for this plane, to sketch it, okay, so take a point, okay, or say put y and z are zeros. What does that mean? That means we are on the x-axis. Okay, so here, this value is 1 on the x-axis. Similarly, for z and y, okay, we have 1s. Actually, I say 1, but actually it is 1, 0, 0, because the others are 0. This is 0, 1, 0, and this is 0, 0, 1. Okay. So these 3 points are obviously on the plane. It's a plane, so 3 points determine the plane. So we don't have to work too hard. So this is necessarily the plane determined by this triangle. Meaning, if you extend it as a plane in all directions, you get your plane. So this is the graph of f. Okay. So it was a well-known example because we considered planes before. Okay. Let us now make a slight diversion and say, let f of xy be y minus, let me see, do the correct thing. That would be, my example, yeah, x squared minus y. That's, it looks easier, so, okay. Well, it's a polynomial of degree 2, okay. Actually, it is a quadratic surface, but we didn't sketch it, so we can. Well, of course, that means z is x squared minus y. Because the z value, if we look at the graph, is nothing but x squared minus y. So this is the case. Well, what we have, of course, when z is 0, is y is x squared. Okay. So it is something like this. It's a parabola. Well, let us go a little bit higher. That's to say, z is z1, but positive. Then, of course, we get z1 is a positive number now, so y is x squared plus z1, but this being a positive number, it's a shifted parabola where y is larger. Okay? Because you raise your y a little bit, so it will be something like this. On the other hand, if you go down, okay, if z is z2 and it's negative, then y is x squared, okay, plus z2, but this is a negative number. So you are pulling your parabola down a little bit, okay, along the y-axis. So it would be something like this. Okay. Now, if you connect these endpoints together, okay, you will see that they are the intersection of the surface with zy plane. Okay, that is x is 0. So the points, let me color them a little bit. So gamma, the intersection of the surface with the z x plane, y plane. Which means that x is 0, okay, is z is minus y. So it's a straight line. So now the figure is clear, okay. So the graph is